this is it. This is the end of the lecture. And I would like to summarize a bit, but now in a transversal fashion, what we have been doing in the lecture. And I'd like to go again through these 10 top principles of big data to make very clear on the high level. We looked at a lot of technologies, right? It looks like every week there was something different. It's all connected. It's all connected. Yes, I'm watching Netflix. It's all connected. And the technologies that you are learning here, you can extrapolate them to other technologies. So it doesn't really matter that we use this or that technology. It's all the same. If you want to learn another one, for example, you started with Spark, there are alternatives to Spark, right? There are other processing engines. There's Apache Flink that can do streaming as well and so on. It will be very easy for you to learn. You have the basic principles. So in a way, the technologies that we use, they are only some proxy to learning things. We look in detail at the technology, but it's the big picture that is very important. And the other thing that it's all connected throughout the weeks is that these data shapes, they have a lot in common in the way that it works in the architecture, right? So if we start learning from the past, tables are here. They will not disappear. They still cover many use cases. In the real world, that's the first thing you should think of. You have highly structured data, not too large quantity, go for a relational database. Without hesitation, that's always the first thing that you should consider, and you need to ask yourself the question. Of course, you know how to do big data and so on. It doesn't mean you should use it everywhere. So tables are here to stay. And it is absolutely fundamental that you understand that there are data shapes, right? So there are cubes, there are trees, there are tables, there are graphs, there is fully unstructured data. Text can also consider pictures, videos, audio. It is absolutely important because when you have the shapes, this is where it all starts. You have the shape, you build a model from the shape. We even saw you can have multiple models for the same shape. For graphs, for example, there's several competing models. There's the labeled property graph. There is the triple store. So you can have multiple models for the same shape. And once you have the shape and the model, all the rest follows, right? The query language, the syntax, and so on. So it is absolutely fundamental to at least recognize that these are here to stay, these shapes. I cannot fully exclude, we have to have an open mind. It might be people find other shapes that we can add to the list, but a shape is so fundamental that this is not the sort of thing that will happen every day, if at all. You could almost consider with machine learning that tensors could be considered a new shape, but even if you think a little bit, really a new shape could maybe still fit in there. So it's a good question to ask, right? So these shapes, cubes, graphs, trees, tables, and unstructured data, they are here to stay. The second thing that is very important is to keep things simple. When you build a big system, if you do it too complex that you cannot understand it anymore, you will not be able to manage it anymore. So you have to keep things simple. And if you see a lot of the technologies that we've seen, they are actually relatively simple, at least in the model. Even HDFS, it's a complex architecture, of course, but in the end, what is it? It's a file hierarchy organized in directories, and the files are split in blocks. That's pretty much it. Then, of course, there's the physical architecture and the implementation, but the design is relatively simple. In MapReduce, just collections of key value pairs. And then we have a first phase, then we shuffle around, we have a second phase, we get back a collection of key value pairs. Spark is the same idea. You have RDDs everywhere, right? It's a big collection of stuff, whatever that is. And then you just have a restaurant menu of transformations that you can apply to these collections of stuff, and then you get something at the end. So you see the design is really simple. The architecture is going to require some work, but on the high level, it's actually simple. So I like to quote Albert Einstein here, that we should make everything as simple as possible, but not simpler, because of course, then it doesn't bring you anywhere. All right, the third insight, but as computer scientists, I'm pretty much you were already convinced of this before the lecture, is to modularize the architecture. You're doing yourself a service, but also other people, because this is also how you can collaborate with other people. If you have a modular architecture, everybody just maintains their parts of the architecture. So every data shape, and it doesn't matter what it is, the cube, tree, cube, tree, graph, table. I would almost say text. If you visited the information retrieval lecture, you might even recognize that even for unstructured data, that still applies to some extent. You have a whole paradigm, meaning what is the shape about? For example, the table is made of rows and columns. What's the data model? So in the relational model, for example, is the idea of tuples, that you have sets of tuples. You have the idea of a syntax. You have a query language to query that specific model. You have an architecture, but you can have multiple architectures, of course. You can have several ways of implementing the system. We saw you can do it natively from scratch, but you can also implement a system on top of another system, might be easier. And that's where the mapping to other shapes are actually coming. So let's now kind of summarize things, right? All of these shapes that we've seen. The data model is basically saying everything is whatever. Everything's a cube, everything's a table. I'm not giving the details of the definitions for simplicity, but basically you say everything is that, and then you say what you can do with it. A cube, you can slice, you can dice, you can aggregate, roll up, drill down, pivot, cross-tabulate, and so on. A table, you can select on the rows, you can project on the columns, you can rename, you can group, you can join, you can sort, you can union. This is the relational algebra. Trees, you can look up in an object. For example, if you have objects and arrays that make up your tree, you can navigate down the tree. We saw with JSON how we can do that. We can normalize, denormalize the data, right? It's about joining or unjoining, kind of. You can nest or unnest the data. You can validate data, because in a tree, it might be not validated yet, as opposed to a table. And of course, you have much of the relational algebra that works on collections of trees as well, right? Selecting, projecting, grouping, and so on. Graphs, you can traverse the graph, you can find patterns, as we saw in this ASCII art-like language, in the query language, Cypher. But you also have some features of the relational algebra. You recognize some of the clauses in the language that you can select, you can filter, you can sort. Some languages support group by. I don't think Cypher had it, but in the Oracle guest lecture, you might have seen a group by there. And text even has a paradigm, right? This is information retrieval. It's not part of big data, but you can filter the text, you can map it when you can build the standard inverted index by grouping, aggregating, and so on. So this is all about the data models. And you see everything starts with the shape that you have. This is the absolute first question that you have to ask yourself: what's the shape of my data? If you get this wrong, then you risk being very slow, both productivity and performance, if you don't get this right from the beginning. Next comes the syntax. We saw for cubes, we have XBRL. There's others, of course. For tables, there's CSV, for example, even though many admins prefer to export to SQL scripts rather than CSV for some other reasons. Trees, we have so many. XML, JSON, BSON, Parquet, that's a binary format, Avro, protocol buffers, and so on. Graphs, we have RDF over XML, Turtle, and so on and so on. Text, well, that's already kind of syntax, right? So this is why I didn't put anything. But you kind of see the patterns here, right? We have all these shapes, but in the end, what we do with the shapes is on the high level the same thing. It's just that we need to fine-grain the details for every shape to address its specifics. Shapes have query languages too. Cubes have MDX, even though I only showed you a quick example of that. You're not supposed to know MDX. Tables have SQL. Trees, again, so many languages. I'll come back to that. JSONic, query, AQL. There's two AQLs, actually. Arango query language and Asterix DB query language. There's Nickel, there's Uncle, there's Particle. That's a newer one. There's GraphQL. That was also invented a few years ago. Graphs, there is Sparkle for RDF. There is Cypher for the labeled property graph. There is GraphQL. There is also the Oracle one, which is PGQL, if I correctly remember. And text is basically your own code, but if you remember, those of you who are in information retrieval, that's the query language that we use. That's, for example, phrase search or Boolean search is another example of query language. But you see, every shape has its model, every shape has syntax, every shape has its query languages. And of course, now you see the evolution, because tables have been there for so long that there is an undisputed language. Here it's a whole other story. The markets have not consolidated yet. There's still a lot of work that will need to be done to consolidate things and maybe agree on some standards that people can follow. Okay. The first principle we saw is homogeneity in the large is the idea that at very, very large scale, the best way to think about it is to just chunk the data, and that's pretty much it, right? So the reason for that is, as I showed you in the very first lecture, the big starting point of everything in big data is that now we can store enormous amounts of data, we just cannot read them fast enough. That's the real problem that we have. This is how we solve it with parallelism. And the latency is even worse than throughput. So for the latency, it went down, right? Not up. So this went up, the latency went down. But the problem is that now we have also between the latency and the throughput the same discrepancy. So as you might remember, we solved that with parallelism. So we look at huge collections of billions, trillions, quadrillions. We just cut them into chunks. This is fully homogeneous, right? And throughput and latency, I'll come back to that. It's batch processing, right? So again, I repeat, whatever collection you have, collections of trees, even a graph, even whatever you have, you just scale out by organizing it into chunks, into partitions, into splits, into blocks, into whatever you call it. There's plenty of synonyms. And this is how you scale out. Why? Because once you have the chunks, you can spread it all over the cluster. That's the way it works. And this is the parallelism that we introduce because of this right here. This is where the parallelism helps. Okay, next, heterogeneity in the small. This is when you zoom in. If you zoom out, you have quadrillions of stuff, you just cut it into chunks, fully homogeneous. If you zoom in on individual items in your collection, then there's diversity. Basically, every item in there can be absolutely different. And this is why when you denormalize data and look at collections of trees, this gives you this flexibility to account for the diversity of the data, right? So you go from tables to collections of trees, and now you can mix and match plenty of types. And this is a table, actually, it was one of your predecessors a few years back that asked for this correspondence table that you already saw in the data modeling lecture. But you see, we saw that there's all the types the data can have. It's still limited in the sense that it's pretty much the same everywhere, can be different. But with heterogeneity in the small, you can mix these things. You can have in the same collection a few doubles, a few floats, a few objects, all intermixed. It all works, right? This is very different from the relational model where every single row of your table has to be exactly the same as every other row, the same columns, the same domains, and so on, right? So this is one of the benefits that is unlocked with collections of trees, is that we can merge all of that. And this is why we need schemas, because again, you don't need them for relational databases because it's forced from the very beginning. But if you have collections of trees, you still need to do it later, right? You can come up with a schema to validate your data later. Okay. So when you have data in the small, you might need to parse the data to memory, to serialize it back. You can validate your data, you can query your data. There are so many formats. Now it's you can do it as a data lake using XML, JSON. You can validate with XML schema, JSON schema. XQuery is the XML equivalent of JSONic, Parquet, and so on. So these are all, now you know what all this is, right? These are syntaxes, validation languages, binary format, query language, and so on. Okay. The sixth point that we had in this top 10 is the abstraction of the logical level from the physical level. And I think I insisted on that almost every week. I never stopped insisting on that. Almost every week, I gave you the logical model on the high level. Usually it was relatively simple. And then we moved on to the physical implementation. Usually the physical implementation was maybe not so easy anymore, right? Because this is why it gets complex. For example, in HBase, this whole thing about the stores and the log structures, merge trees, and so on and so on. But what's nice is that it's hidden. The user doesn't need to see that. You, as computer scientists and future data engineers, might need to understand that because you will actually work on these systems. But the users, they don't need to. They don't need to worry about these things. They can just focus on, you know, the shape of the data in the model and the query language, right? So in other words, whenever you implement an engine and you implement, for example, on the physical level, you implement a join, you implement a group by, you know, in the system. Basically, what you're really doing is that you're doing it once and for all so that nobody else ever needs to do it again. You did it for them. and then it's done. And whenever somebody does a join or does a group by, it will execute your code. This is very different from a system. Today, for example, a lot of people just directly write Python or that sort of language. But then what happens is that many people just write thousands of times the same thing. They keep re-implementing the same algorithms all over again. The whole point of a logical independence, of data independence, is that you no longer need to implement things multiple times. And one other benefit of this data independence is that you can reuse components. And for example, we saw for cubes that they are very easy to implement on top of tables, because a cube can be expressed as a facts table, where every row in the facts table is one cell of the cube. This is very natural. And that means that if you want to implement a system that manipulates data cubes, start with a relational database. Take that as the physical level. So the physical database becomes the physical level for your data cube model, and then you hide that, and the user sees cube. It's going to be much faster than doing it from scratch. There are people who did it from scratch. It's called MOLAP, but it was much more work than to start with a relational database. There are plenty of other natural mappings. For example, a table can be very easily converted to a collection of trees. It's easy. It's just a collection of flat and homogeneous trees. Trees can be converted to graphs. It's easy, right? A tree is just a graph without directed cycles. A graph can be converted as a table. Think the triples, right? And text, well, you basically can imagine all the directions in which that goes. But then, of course, it's transitive, right? You could implement a cube on top of a table, then the table on top of the tree, and you got a cube on top of a tree, right? But again, careful with that. Whenever you introduce a level of indirection and you try to fit a shape on top of another shape, if you don't do it correctly, this is going to be slow. Right. So this is the reason why many systems actually are in the end up being done natively in order to get the best performance that you can get. Right. But it's a good idea if you understand that these are the natural mappings that are relatively straightforward. Okay. So the architecture, by now you probably realize that there is this hidden storage, ideally. That's unlike a data lake, that the user doesn't need to worry about the physical storage. There is MapReduce and Spark-like technologies, or maybe their successors, but they are hidden from the user. Right? This is the kind of my wish list for the future, that they are here, they parallelize, they batch process, the users don't need to worry about that. All the users worry about is a fancy declarative language, SQL, MDX, and so on and so on. By the way, that language can even be voice. Imagine the voice assistants and so on, you know that this is going to evolve, right? Okay. All right, and this is a reminder of the language landscape that I showed you in the very first lecture, where you have the software engineering languages with the low level with assembly code and higher level with C, Java, and so on. Then you have also for databases, the low level and the high level. So the low level would be the frameworks like Spark, MapReduce, and so on. So here it's more like an API that you need to use manually. So it's more like the assembly code of data. And then you have the higher level languages like SQL, MDX, JSONic, Cypher, and so on that work on a higher level. And here, this is for the future. What I would very much love to see happening is that we have these low level languages for machine learning. If you think of TensorFlow, PyTorch, and so on, this is what it is. It's a bit like the same as Spark, except that it's for machine learning. And there are people working on the equivalent of this and this, of Java and SQL for machine learning. It is also research with the hope of no longer having to actually use TensorFlow or PyTorch or anything. You would have a higher level language that specifically works on machine learning. I think this is one of the examples that I found, but there are probably a lot of people trying to achieve that. Right. In particular, in order to showcase this and have a unified framework for the lecture, with more than 20 students, by now we built at ETH this engine, RumbleDB, that you use in the exercises on your local laptop. Every time we try new things, of course, we need to fix a few things, but this is because we push it a bit more every semester. I hope that you all managed to make it work. The only problem that I was aware of is that for some of you, you run out of memory. If you had only 8 gigabytes, it's simply because the standalone jar, by default, when you run it, it's only taking, what was it? Was it 1/4 of your memory or something like that? So if you don't tell it otherwise, it limits to 1/4 of your memory. So you have to manually add something that says, hey, it's fine if you use more than 1/4 of the memory. That was the main issue that I saw that you people had. The other one was Docker M1. So this is really something we'll continue to look into. It seems the problem is not gone. We had hoped that the problem would be gone after more experience now that the M1 cores have been out for a long time. But this is the top priority of the TA team and the next semester's TA team that will look into this M1 issue for Docker. Okay. And then I don't need to say much about that, sharding the data, replicating the data in order you lose it, and by lots of cheap hardware. These are all hopefully automatic thoughts that you have now. The decentralized architecture, except in some of the systems like DynamoDB, but most of them are fully decentralized. Sorry, where did I put decentralized? Yeah, I mean centralized. HDFS, Spark, MapReduce, and so on. Every time you had some coordination, so a central node, and then all the workers that are processing the tasks, right? So it's a very common architecture to have a centralized architecture in many clusters in big data, right? Okay, and finally, the last point was batch process. Batch process is really the idea, instead of doing things one by one, you put them in groups, and then you do it one group at a time, one batch at a time, right? So HBase stores the data that way. You accumulate data, and then you flush it to disk. You let several files be created, and then you compact them, right? So you don't keep doing it all the time. You wait a little bit until it accumulates, and then process everything at the same time. This is called batch processing. So you, in the future, some of you will work in data engineers in companies. Some of you will be users, but a lot of you with design things. So you will have no problem learning an existing product that wasn't covered in the lecture. You have the basic principles. We'll just look at the documentation, and you will just be able to map the concepts, maybe learn a few new ones. You will have to choose which product to use, again, based on the shape, the size of the data, and so on. And some of you might even be the lucky ones who will design whole new technologies and products that will be taught in 5 or 10 years in universities. And I'm really looking forward to seeing that, what you will contribute in the future. So in order to make these decisions, whether you need a new system or even choosing the product to use, you need to look at the shape. I cannot emphasize that enough. The size of the data that you need to store. Does it fit in a disk? Do you really need a cluster? Do you have a disk I/O bottleneck? And what do you want to do with your data? Do you want to traverse a graph? Do you want to navigate a tree? Do you just want to filter your data? You know, all of that also in the end tells you what query language you need, what functionality you need. What's super important is to not reinvent the wheel. In databases, it's absolutely saddening how many people keep reinventing the wheel all the time. This is sad, because this is wasting resources, right? If people have already invented things, try to reuse this. It's reusable components. It's a whole landscape. Very often you can realize that people had the same problems before, and you can just recycle what they've been doing, or you can reuse the tooling or the ecosystem to get what you want to do. So this is really, if you are at the bottom of this pyramid here, you really need to know that this is where you are, and you need to be able to justify why it is that you're coming up with a brand new product and that what existed before was not good enough. It's very important that you're able to tell that, especially for those of you who do a PhD at your defense. If you're not able to justify, this is bad, right? You really need to be able to make a case. And this one also, this is still tied to the wisdom. Even if you know big data, you know how to use clusters of thousands of machines, you know how to query petabytes of data. But nevertheless, in many cases, you create a startup, you start a system, you can do it on your laptop. In many cases, it just fits on your laptop. You just need to pick the right formats, compressed, efficient, and write good code. This is going to work. this stops working at very large scales, but then it's really because you don't have any other choice. You have so much data that you're really at these scales. Okay, so here I'm just repeating this whole thing. This is the graph I showed earlier, capacity, throughput, latency. The discrepancy between them is what drove this whole big data evolution, right? So what's in it for the future? I really don't know. I can maybe share a few thoughts. It's actually been evolving a lot because I've done it for a few years, and now some of the things actually now start happening, which is really great. I mean, it's happening in front of our eyes. So MapReduce and Spark will hopefully be invisible. A lot of companies are working on higher level. For example, Google is working on BigQuery, which is a better abstraction than a lower level API. So hopefully people will one day no longer have to directly use the APIs on the low level of MapReduce and Spark, except the data engineers that are building the systems for the end users. These will still do that, but the end users normally shouldn't have to do it anymore. The data shapes finally will be understood to be central. This is one of the education uphill battles to get people to understand how important data shapes are. I see so many people who have tables, but they still use MongoDB or Neo4j. They have tables, they should use a relational database. This is the most efficient you can get. Another example is the other way around, that people have data that doesn't fit in tables because it's heterogeneous, because it has extra values that are hard to predict and so on, because it's logs accumulated over time over multiple schemas. And they nevertheless take a hammer and try to fit it in a relational database, but it doesn't work. So you really, really need an awareness that the data shape is the source of all the problems you're going to have in terms of productivity and performance, but it's also the source of the solutions, if you are aware of that from the very beginning. My wish list is also that the query languages will at some point consolidate and get standardized, just like SQL for tables. We are still a long way from that for the other shapes, but probably it will happen in the end. And there are even people trying to unify everything to have a single language that does all shapes. It might actually end up happening. I think there was a term called polystore that was cast at Microsoft. I had the name, but I just slipped off my tongue. Okay, so W3C is one of the instances where, for example, they standardize, but there's also other like ECMA standards is another one. So XML, for example, is W3C. JSON is now an ECMA standard. Okay, because the problem we have, I don't know if you know this explicitly, but the problem we have is that every time it's the same. There's all these languages, then people arrive and say, okay, we have all these languages, what do we do? Let's build one that unifies them all, right? And there you go, and then you just end up with these new fancy websites that advertises your super new language that solves absolutely everything, except that you just end up adding one language to the list. The only way you get standard is to get people to sit together around the table from all the companies and talk to each other. In a way, this is what was done for SQL. This is also what was done in the case of xQuery right here. That was really done around the table. It shares a lot of DNA with JSONic, but hopefully this can continue. It's not easy at all. In order to sit around the table and disagree and agree to disagree takes a lot of diplomacy, a lot of patience. It takes years and years and years in order to agree on things. That's absolutely gigantic work. But at the end, when you have a standard, it really pays off. Right. UIs are probably going to gain in importance for the users, maybe even talking over voice, because many users are not able to code, right? So SQL is already more intuitive, right? But in the end, you still need an interface that most people can actually understand. So the voice assistants are kind of going in this direction. It was a hype a few years ago. Now I think it's slightly out of the hype, but usually when it's out of the hype, maybe that's the sign that it's just gonna silently come back and become normal, who knows? Of course, I'm not mentioning this whole data protection thing. This is orthogonal, and that's also extremely important, data protection. I will come back to that. Data might also be fully fungible to the point that you can just, like water, can just exchange data like electricity or, that's the case actually if you think of XBRL and RDF, they are that in a way. RDF is just a huge collection of triples. Triples are kind of fungible, and the same for cells in cubes. Data and money might converge, even though that hype is also starting to get a bit old, just going through its ups and downs the whole time. But in the end, the realization that money is in fact just data that keeps track of who has what, then there is also something interesting going on here in both directions, not just the direction that you use a blockchain to store money, but also the direction that data itself is a means of payment, right? When you use a system that collects your data, you're actually paying with your data. That's also the reason why now we have GDPR and, a lot of laws that are put into place in order to try to protect privacy and data protection. It's out of the scope of the lecture. There's other lectures like Big Data Law and Policy talks about this, and I recommend following these as well. We are going to soon go to the break, maybe just a few slides, then I will give you the full 15 minutes. So yes, this is what's going on right now. It has a lot of impact, for example, on the location where you put the data. You cannot put it in any data center. It's important. Is it in Switzerland? Is it in Germany? Is it in the US? 10 years ago, nobody cared really. But today, everybody cares. It has become central that as a company, you know exactly where your data is stored, so that you have control over it. Something interesting is also happening between machine learning and databases. And what's very funny between the two is that they are both trying to eat each other. So there's database people trying to eat machine learning, just add machine learning functionality to a database, for example, a relational database. But on the other hand, there's the machine learning people who are trying to rebuild the entire database system, replacing everything through machine learning. For example, one topic is the topic of learned index. Instead of a hash index or a B+3, you replace it with a machine learning model that just learns and tells you where the data you're looking for is, right? So this is called the learned index. And so there are people who are trying to slowly do that. And at MIT, one of my former colleagues, he was here at ETH before working on that sort of things. All right. Then quantum computing is a topic I will probably not say much there's plenty of lectures on the topic if you're interested. It's very hard to say now where it's going. Will it succeed? Will it not? I frankly have absolutely no idea. But if it does, we'll have to implement relational database systems on top of these. And this is going to be extraordinarily exciting, I think, to re-implement all of that on quantum computers. And hopefully some of you might do that. Yeah, and finally, just very quickly, there is this Web3. I don't know really what to think of it, but I can give one small perspective in terms of big data, what it really means, is the idea of decentralizing the providing the services. For example, S3, Azure Blob Storage, these are all cloud services, but they are provided by a single provider. And part of the idea, as I understand it, of the people who are defending the notion of this Web3 with the blockchains and so on, is to decentralize that. And there is, for example, a system just like HDFS or S3 called IPFS. It means Interplanetary File System. It's a very fancy name, I know, but it just basically is a decentralized way of storing the web, right? You no longer need to go to a cloud provider. I also have no idea if this is going to succeed or not. But it's good to know that this effort to try to decentralize things is something that some people are pursuing, and we'll see if that works or not. So now, before we take the break, I would like to take some time to thank all of the TA team who did the lecture with me. So Lam is right here. We have Fabio. So big applause for, yes. Is there any other TA in the team, in the room? Maybe the curtains would like to teach as well. All right. I think you all deserve the break. So right after the break, I'd say a few words on the exam, then we'll start the quiz. It is 5:03, sorry. So we'll start at 3:20, the second half of the lecture. Yeah. See you.